All right, so welcome guys back to lab session number 6 of the deep learning course, where today we're going to be continuing our discussion on natural language processing. And today we're going to be studying transformers and also continuing our discussion on NLP in general because it's a very wide topic. So I think it's only fair that we spend at least 2 labs on this. So last time we actually left on LSTMs, for example, and we also still have to complete a training loop. So actually, let's take a look. Let's actually go back and recap what we studied last time. And once we're done with that, we'll study what transformers are. All right. So we actually built a very simple, what do you call, text prediction model, right? And it all the simple task that we gave it to it was we gave it some numbers sequentially 1 2 3 up till 10,000 I think, and then its task would be to take in certain number of terms, certain number of words, and then predict the next sequence of words. So if I give 1 2 3 as the input, it's supposed to give me 4 as the output or something like that, right? So we actually built a data set for that and we named it sex, seqs, sequences. And so first we gave each individual token a specific number because computers only understand number. And so 0 1 2, 0 represents 1, 2, the word 2 represents the number 1, and then 1 represents this dot that we use to separate each different term. And so it's 0.1, and the output would be dot. Corresponding input would be dot 2 dot, and the output would be 3. uh, 3.4 output would be dot again, and so on and so forth. We divided this into what do you call training and testing data sets. We uh, disabled shuffle because we wanted to be sequential in nature. And then we started building our RNN. Now, apparently, there was some problem in our training loop. So let's actually run this again and try to solve that first. And I already have shared this notebook with you, and will share it again on the course website so everyone can take a look at it. Uh, okay, let it run. Right. All right. So we have this. Let's run this. And let's actually take a look at our RNN model now. Now we will slowly make all these changes, but let's actually go sequentially because we would be iterating through it a lot of times. We would be slowly making changes and trying to improve the results. So the basic idea of this is that there is an initial layer that first creates embeddings for each token because one token is very sparse and it does not have enough information to create any meaningful results. And so we first, corresponding to each vector, create an entire another vector which contains enough information to do that, and that is trainable in the entire loop. So that layer is called NN.embedding. We do some processing after that, so those are hidden layers. And the final whatever activations you get, you pass it through one final layer, which is gonna output again the one hot encoded type of vectors, basically, which will be of the size. The length of that one hot encoded vector will be vocab size, right? And this will actually basically just be activations. And so what we need to do after that will be like whatever has the maximum activation, we're gonna say that that is the prediction of this model corresponding to that word. Um, this hidden layer in the middle is just nothing but a linear layer. It can be multiple layers. It can be an entire neural network on its own, but it's essentially just a processing unit, right? And what we do for the forward loop is that we define this variable known as h, which is nothing but the intermediate value, hidden value, or whatever you want to call it. And then because there are three tokens within this input, we're going to go with each of them. We're going to pass it through that embedding layer followed by that hidden layer. And then it again goes through the hidden layer again and again. And whatever comes out finally after three tokens will be passed through the output layer, and that will give me the output. All right. So that was my RNN model. And let's actually this. So I use this learner function from fast.ai. I've not defined this on my own this time because I want to use some more functionality, which I will show whatever we're going to use. But this is not very much different from what we've already built. And so my purpose over here is that we simply learn how to use APIs in a very fast and efficient manner. So in minimal amount of time, you should be able to catch up with any new library. And yeah, it trains, and we have about 50% accuracy. We actually, I think we reached this point. And you might say that this is not very good, but it is. It's not very bad actually, because uh, given that it's a relatively very small data set, we have a very low complexity model. I don't know how many parameters we have, but uh, let's say there's a completely random model that has not learned. It gives only about a 3% accuracy or so. And let's say that even if the word which was present the maximum amount of times, which is the word thousand, because 1001, 1002, 1003, it keeps on repeating so many times that even if that was predicted so many times, that we would still have an accuracy of about 15% or so, which is still not good. Having said that, 50% accuracy is not extremely bad when it comes to language models. And as I said last time, accuracy is not really a good measure of what do you call language models in general. We use different sorts of metrics like perplexity, and we'll talk about that in a bit. But all right, um, let's actually try to improve this a little bit. Now, what essentially I'm trying to do over here is here's the problem that this model at the top raised, which is essentially that you see that at the beginning of each input we set this h is equal to 0, which is nothing but the hidden state of the RNN, right? It contains all the activations corresponding to uh, let's say any input. So one is passed through that hidden layer, and it and then whatever activation comes, that again goes through that hidden layer to create uh, along with the input 2 to create some other value, and that again goes into the input with the input 3 to create another value activation. And so this h contains activations or like information from an entire sequence. But the problem with this is that, like, with each new input, we're essentially just throwing it out, which is not good. I mean, like, how good would it be to have a model that can? I mean, why should the output, let's say, 131 only? I mean, why should the output corresponding to this output only contain activations from these three values? Why not? I mean, which is essentially just like 2.3 dot 4, for example. 4 is the output, let's for example, and it contains only information about 2 dot and 3. Why not it contain information about 1 as well? And why not it contain information about like all the previous ones as well? It will only make the model better, right? Like, so for example, if I were to predict like 61, it contains information like activations from 1 to 360, and that will only increase the efficiency. Like, for example, like, this is a very small toy example, but when you're talking about like long term dependencies, like, uh, like, we start a word like, for example, Palash went to the market and he bought three oranges, right? And so when I'm talking about the word he is actually very much dependent on the fact that we assume that Palash is a male, and that information only comes with Palash. And now suppose I were to replace it with something like Jennifer, and then he would now have to be replaced with she, right? And so unless we have dependencies from longer from sequences, there's no way that you're going to be able to determine whether it's a he or a she. And so it's very important to retain the state of the RNN as we go through these sequences, right? So a good way to do that is that what we're going to do is that we're going to make h a parameter of the class itself, an attribute of the class itself. So we're going to say self.h is equal to 0. And so what's going to happen is that now I don't need h is equal to 0 over here. And what I can do is that whatever previous self.h I had, it can simply be continued over to the next sequences, right? And that's going to be here. But there's one problem that we need to solve over here. That is that because now we have activations from, let's say, 10,000 words, the gradients, so I mean it all is being like connected to the computational graph as such, right? um, so what essentially happens is when you do back propagation, it's going to propagate all the way back to, let's say, the very first input that was given, that was say 1.2.3, which is simply not required. I mean, uh, we are not trying to, so I mean the problem is that whenever you have 415 as the input, one should be the output. So the gradients also must be calculated restricted to that itself, because that means that whenever the input is 415, the output should be 1, and the model should learn to do that without any other sequences. I mean, we're training it with the help of previous sequences as well to make it what do you call, identify dependencies, but it should not be reliant on that, right? And so uh, what you are doing essentially with this, by not throwing out, by not making h is equal to 0 at every step, is that you're telling the model that in order for the model to predict this one, it needs to be provided input all the way from 0, 1, 2, 1, 3, 1, 4, 1, 5, which is not right. So the gradients, I mean, because which is whatever amount of information is required for that, weight update or whatever, must be stopped over here itself. And so what we do is that after each input, we're going to detach this edge from the computational graph. We're going to say that, well, the activation stays self.h, the value doesn't go anywhere, right? Self.h still has that value, but it's not no longer in the computational graph, and so it doesn't like contribute to gradients anyways. So for that, what we do is that self.h is equal to self.h.detach. That's it. All right. And I'm gonna define another method over here, which occasionally resets h back into zero, which you're gonna need to do at the beginning of each training epoch, and then at the beginning of validation or in during each epoch, because like training and validation are two completely different things. So you can't retain the h self.h. Obviously, you need to reset it to zero. All right. Uh, that model is actually gonna work as is, but there's one thing that I want to do before that, one small change, which is I actually want, now since we're talking about sequentiality and we're giving so much focus on the sequentiality, let's also talk about another thing, which is that uh, did you notice that uh, till now we didn't actually consider like uh, any other, we didn't consider sequentiality as such. I mean, we only trained the model completely on the fact that whenever 415 is given as the input, one should be the output. That was entirely the basis of the model, right? It never considered the sequentiality, like that after 012 comes 131, comes 415 after that, and then comes 161, and so on and so forth. And so now we need to actually make sure that our model we need to actually make sure that the data is fed in such a way that sequence is maintained. Now you might think that we've ensured of that because when we built a data set, we built it in a very sequential manner, which is, let's say, I mean, huh. So this sequences, for example, was very like sequential in ways like we didn't shuffle it. We ensured that shuffling was not taking place, but we actually missed a very small loophole, uh, which was that when we concatenate or when we put different inputs into a batch, I mean, each term, the way neural network models work is that each term in the batch is considered separately, right? Um, oh, I'm sorry, I wasn't sharing my screen. Just give me a second. Right. Uh, anyways, uh, yeah. So I was saying that yeah, we the way neural networks work is that they consider each element within the batch separately, right, independently, and what essentially happens is that if you go to the C++ layer, like CUDA layers, you'll find that it's a simple C++ code. It goes iteratively over everything in a batch and passes through the neural network models, concatenates the output, and gives it back to you. Like that's how it works. Right. And whenever you want to do gradient descent, it will again go through the for loop and then do an average or whatever, however you define the training loop. But now, so of course, if you wanna ensure what do you call sequentiality, you will have to take some other measures. So the way we're gonna do this is we're gonna rearrange our data set in a new way. And let me show you what I mean by that. What should I open? What should I open? Jamboard. Hmm. Plus, yeah. Uh, let's say these are my tokens corresponding to the word. Where's my text box? One, two. Sorry, one dot two dot three. Oh god. 3.4.5.6.7.8.9.10. All right. What essentially happens now is that um, yeah. So what essentially is going to happen is that uh, by default 1.2 dot sorry 1.2 is one input, 2.3 is one input. Sorry, between that there is 2 dot 2 dot anyways. But these all are considered independently, and so what we actually need to do is that between different batches, so we need to arrange it in such a way that the model identifies this sequentiality. Now of course it cannot stay in one batch because one every element in a batch is considered independently. So what you need to do is that you need to ensure that there is sequentiality between different batches. Do you get my point? That when batch one comes, you give it 1.2, and then when the next batch is given, you give it dot 2 dot, and then whenever you get the third batch, you'll get 2.3. That's how it should work. So what I'm going to do is that what the new what do you call data set would look like is that 1.2 should be present in one data set. This is the next data set that's going to say 2.2 dot whatever, and then the third batch is going to be 2.3. Now, of course, a batch contains multiple elements, so the I mean, I'd assume that this much amount of sequentiality is enough, and of course, depending on the number of batches, there is going to be that much sequentiality. We're going to maintain that much sequentiality, and whenever we reach to the end of number of batches, we're going to come back to the first one, and so we're going to come back to the first one and say that 3.4 is going to come under this batch, right? So the first batch doesn't contain 1.2 and then dot 2 dot. It contains 1.2 and 3.4. And the second batch contains like, so we're maintaining sequentiality across different batches. So this is what we need to do over here in order to maintain the sequentiality, in order to tell the neural network model that this is how it's supposed to what do you call maintain sequentiality. This is how you're supposed to identify sequentiality, right? We didn't actually consider that last time, but now we do need to do that. Anyways, so we define something known as group chunks, which is we first divide them into chunks and then we group them appropriately. So in we know number of batches that we're gonna have. We define it. It's a hyperparameter that we define depending on the size of capacity of the GPU and whatnot. So let's say it's 64 or whatever. All right. Um, and let's say so within each batch there is going to be certain amount of elements that we need to define. Yeah. And that is going to so sorry within each batch there is certain number of elements, so number of sequences that we're going to define is going to be nothing but total number of elements, data set, data points that we have, integer divided by the batch size. So I mean, by the way, if you don't know, this is called a batch, right? And then this will be m in number, like these will be m in number, right? Anyways, uh I did that. The reason I didn't do a float divide because number one, how will you divide anything by float? And also the purpose of this divide is to actually make sure that uh, in the end, let's say there are less than the number of like there are not enough elements to fill the entire batch, so we're gonna drop that data point as well because the like there is image augmentation in like in images in which you can use to like fill a batch. So bats, like this isn't a problem, but you can just simply generate random text, so for example, so the best idea is to simply drop that last batch which does not contain enough data points to fill that entire batch. uh, all right, so what I'm going to do is that I'm going to create a list. L is nothing but a fastAI property, which is a modified list, a sort of more advanced list. And what I'm going to do is that I'm going to go sequentially, and I'm going to jump. What I'm going to do is that within each batch, if I'm doing, if I first put zeroth element, then the next element will be like m times like m data points. The next data point will be the data point that occurs m steps after the zeroth element, and then 2m elements after that, and 3m elements after that. And the next batch will contain element 1, and then the element m plus 1, and then the element 2m plus 1, and so on and so forth. Do you get the point? And I'm just simply going to return that new data set. And let's actually see what that looks like. So initially, if you remember that the data set looks something like 0, 1, 2, 1, 3, 1, 4, 1, 5. Now we have actually rearranged it, and now one batch looks something like 0, 1, 2, 1, 11, 1, 2. Output will be 28th, token 2, 25, 7, 1, and so on and so forth. So we've rearranged that. Anyways, uh, I've already defined, like I've already defined batch size, and so I've already defined, I've learned about M as well, and so yeah. Anyways, I'm gonna create new data loaders out of that. Oh, I haven't run all this, by the way. Give me a second. Right, and let's actually train our modified RNN, which learns about the sequentiality as well. So, anyways. So you'll see that the accuracy slightly increases. So we have about 52% accuracy, 58% accuracy now, so which is good. 59. So let's say about 60% accuracy. So that's a small jump. That's good. Uh, what's up? All right. So yeah, I mean now that we've included the sequentiality, it's slightly working better now. So that's good. All right. So let's actually go to the next change in the RNN that we're gonna do, and uh, uh, what we're gonna do is that we're gonna increase the complexity of the hidden layer. But till now we've only used like one small linear layer. But what I wanna show is that you can use like an entire neural network in place of it, like an entire like multi-layer RNN, and then we even learned about LSTMs, for example, so we can replace it by that. Um, there's one small thing that I want to do is that first let's actually do two things. One thing that serves two purposes. So let's first increase the complexity of the problem. Till now we're working with very simple like examples, very a very simple problem in which you give three tokens and then you get one token at the output of it, which is supposed to be the next term in the sequence. But what if I want my model to take 16 tokens in the what do you call as the input and output the same number of tokens? And what it's supposed to depict is that like you give 16 tokens and you get the next sequence of 16 tokens. So now instead of one token, the neural network has to get 16 tokens right in order to be right. Right. So we're increasing the complexity by a huge amount. Now there's a purpose why I'm actually doing this. Like you would say that I'm crazy to do this. Why am I even doing this? But uh, there are two reasons. Number one, it's actually easy to handle what do you call this when you actually want to predict data, because otherwise what we'll have to do is that because each input is supposed to be of three tokens and you get only one output, so first you'll have to discard that first token from those three inputs, then you'll have to concatenate this output into those three, so it's some extra code. That is one reason. Second reason is that uh, we actually want to use PyTorch's API. And so if you go to Torch RNN, you'll find uh, you'll find that it takes an input of, let's say, um, I mean, we'll talk about this, but it actually gives the output of the same size as the input. So actually need to factor that in. So we need to modify our data set accordingly. Anyways, uh, as simple as that actually. Mm, so I'm going to define a sequence length, and I'm going to define my data set accordingly. And I'm just simply going to create group chunks with that. And this is what it's going to look like. So 1.2.3 whatever to the output, and the output will be dot 2 dot 3 dot 4 and whatever. So let me create my RNN again. It's pretty much similar, except for the fact that now what I'm going to do is that whenever one is passed as the input, I'm going to pass it through the output layer and ask my model to predict whatever is the corresponding token. And then I'll ask this whatever the activation corresponding to one, it goes back into the model along with the next token, and the output of that is again passed through the output layer to produce the second token. And then whatever comes out of this as the activation is again going to go into the RNN or whatever model along with this next token, and whatever the output is going to be, I'm going to ask my output layer to predict what's the token correspondingly. And so whenever I'm going to reach to the last set of tokens, I'm gonna get all 16 tokens as well as my answer. And so what I'm gonna do is that I'm gonna define a list called outs, and outs is gonna have for each step within the sequence length, I'm gonna what do you call append the activation provided by the HO layer, which is the output layer. It's gonna have and then finally what I'm gonna do is that after of course detaching, because I don't want the gradients from before that, I need to because it's a list, I need to stack them together in a what do you call in a tensor. And so this is gonna have the output batch size, sequence length, and then vocab size. So there are 16 outputs, each is a one hot encoded vector, and there is batch, and there are 64 elements in a batch or something like that. And self dot reset is equal to 0. Oh, I didn't talk about one thing actually. Oh, we talked about it anyways. I was talking about model resetter, but we learned what model resetter does, which is that which is actually the function that will be called at the beginning of training or the beginning of validation to call that reset function that we defined over here. We can actually see what that looks like. So these functions are actually called callbacks. CBs stand for callbacks. Callbacks are nothing but functions called at various stages of the training process, right? In which you can make the function do whatever you want. So, for example, there is a function called before train, which is called, of course, before each training cycle begins. And what it's going to do is it's going to go into the model and it's going to call the reset function. And then before validation, this function is going to be called, and again it does that reset. And after you finish fitting, it's going to reset it again. So that's the purpose of callbacks basically. It's a wonderful concept. It's slightly hard to get, but I mean, I'd really ask you to what do you call go through the concept of callbacks, because it's one of the most important and the like most useful things that you'll ever come across in your deep learning journey. Anyways, uh, let me delete this and let me actually run this entire thing and let's see if this works. Oops, right. Oh, by the way, you must have seen that I'm actually redefining my loss function over here, and it's a very slight variation to what do you call the standard cross entropy loss that we usually do. And the only difference that I'm going to do is that only thing that we actually need to do is that the model by default, right? What it does is that it will essentially do cross entropy on whatever it will not do on the batch size, but whatever is the next dimension based on that. Uh, sorry. So cross entropy actually just assumes that the shape of your output vector will be batch size, comma shape of the vector. But because now this has, I mean, there are three elements over here. I mean, there are three dimensions over here. The batch size is going to simply get confused. Sorry, the cross entropy function. What am I supposed to apply the cross entropy function on? So what we need to do is that we need to actually flatten this entire tensor out, this two-dimensional tensor out, in order for my cross entropy loss to function normally. So that's essentially what I'm doing over here. And you would see that we actually have improved the accuracy to now 65% or so, which is good enough. And now what I'm gonna do is that what did I actually do? So we first just simply increase the what do you call complexity of the problem. The model works perfectly fine. Uh, I had to train it for slightly longer because it's a slightly more complex task now. But now let's actually come to the RNN part of it, which is like multi-layer RNN part of it, uh, which is basically, but instead of the hidden layer just being one single linear layer, I'm just gonna make it multiple linear layers. So increase in complexity, increase in potential, what do you call, improvement in results and whatnot. And some small changes so now we don't have to write that for loop again and again because RNN can take care of that. So this actually comes directly from the API, right? Uh, right. Yeah. So this is the API of the RNN function, and it returns that hidden function, that activation, and the final results as well, which is nothing but one hot encoded vectors. So H has to be detached from the computational graph, and we're gonna pass the final activations from the RNN layer into the output layer, and it's gonna give me the answer. Uh, of course, there's one small thing that we need to do. Now self.h is not a single zero, because you didn't actually realize, but what RNN is essentially doing is that it's passing activations to all 16 of those. Uh, so it's creating a tensor directly out of what do you call a tensor out of these directly 16 activations directly. So zero, which is an integer, and a tensor are not compatible. So you need to actually initialize h as a tensor of zeros of the same size as it's gonna come out over there. So this is what's gonna come out. So there are, by the way, let's say if an RNN has three layers. So of course the first dimension will be three, because each layer is gonna have a corresponding h, and then the remaining is standard. I mean batch size, and then whatever amount of hidden values you have. All right. So uh, right. So you're gonna detach. You're gonna give it, and then this is nothing but the equivalent of zeroing out an entire tensor instead of just assigning the zero value to an integer. So underscore over here means replace. So zero underscore means you replace whatever value you have with a zero in place. It doesn't create a copy. It simply replaces in place. So that's the point of underscore. Look it up. It's a very interesting concept. Right, I did that. And so when I'm defining my RNN over here, I'm gonna have to give an extra element, which is how many linear layers do I want. And I say that I want two layers, let's say for example. And let's actually train this model, and it will train well. Oh, let's actually see. I actually want to show something, which I actually did point out last time, but let's do it again anyways. Right. I trained it for about 15 epochs just as last time, but now you would see that the accuracy is actually slightly worse than what we had in a single layer. Why do you think that is? We got 65% accuracy over here, but only 48% accuracy over here. And so the problem behind this is that there is a problem known as vanishing or exploding gradients, or vanishing or exploding activations in general. And I actually showed you what do you call a demonstration of this, which is uh, you know uh, just give me a second. Yeah, you know how uh, the each linear layer is nothing but a statistical transformation. So what is the purpose of a neural network is to simply learn the statistical distribution of any data. That's essentially what it does mathematically. Of course it learns values, like it can learn specific characteristics, but if you were to go to a pure mathematician, they would absolutely certainly claim that, I mean, it's all about these statistical distributions or whatever data and whatever transformations into that. So let's say that each model has a parameter known as a mean. Sorry, each statistical distribution. So let's say the mean is one, and so I can multiply it as many times I can with as many times. So because each time it goes to an RNN, it's gonna be multiplied by, let's say, a certain amount of value. And if I, sorry, let's say I have, what do you call, an input which has a mean of, let's say, n. Then I multiply it with, let's say, the weight transformation. Like, let's say the factor by which the mean changes is 1.1. Sorry, 1.0. and I can multiply it as many times as I want, 1.0, 1.0. It's gonna stay itself. It's not gonna change. Let's say even if it was like, let's say just 1.1, the recurrent neural networks are sometimes tens of thousands of let's say values apart. So let's say that the initial distribution was 3 or like 1, because we usually normalize the data. But okay. Uh, um, right, right. Let's say 100 layers, it's the activation has now exploded to 13,000. Another zero, it goes exponentially, like e to the power of 41, like e to the power of 41. And let's say 10,000 layers, it's suddenly undefined now. Like it's so huge. And so that's exactly the problem with RNNs, that multiple layers can actually shift the, what do you call, mean by so large, or it can actually diminish time. Okay, let's say this was point 0.9 instead, now just point 0.9, like so nice, and it is now already zero. Like so that's the entire problem with and now you can calculate gradients anymore. So that's the problem with RNNs as such. So which is why we actually defined LSTMs in the first place, and we actually defined this. But now what you can do is that instead of just nn.rnn, normal vanilla RNN, you can replace it with an LSTM cell. And same thing goes ahead, and now you'll actually see that the results have improved quite a bit. Let's see. Yeah, so it's performing now. And slightly random, but you can actually change the um, hyperparameters and as such to actually see that it will even go up till 80% or so, which is like amazing when you think about it. Anyways, that's your normal natural language processing using recurrent neural networks and whatnot. And that's how you create sequential data. Let's actually, okay, but this is actually quite old. I mean, LSTM is like 1997 or such. It's an amazing paper, amazing amount of engineering, but it's dead now. No one uses it anymore. So what you'll see that most people now use something known as the transform. I mean, it's apparently some. It's so amazing. Like, oh, by the way, not this transformer. Uh, right. I mean, so it was actually first introduced back in 2017 in this paper known as "Attention is All You Need" by Vaswani. Um, what a revolutionary paper! I mean, like you must have learned about, you must have heard about like these amazing models, BERT, GPT-2, GPT-3, and they have some amazing amounts of like, they can do like really complex tasks, and it's really scary at times. But I mean, that's the um, beauty. I mean, that's the amount of amazing things that transformers can achieve. And so I think it's only fair that we actually learn how to use them. It doesn't make sense to implement it from scratch, because I mean, again, because now we're actually focusing on APIs, how to use APIs very efficiently, which I think is extremely important. So we're actually gonna be using these models by a library known as Hugging Face, which is, by the way, which is one of the leading startups in the NLP space. Amazing amount of research going on, amazing tools that they provide, amazing courses. So if you want to learn NLP, I doubt you can even leave Hugging Face. I mean, you just can't miss it. Anyways, uh, Hugging Face actually provides us with libraries that give us access to transformers and related things very, very fast, right? So let's actually install Hugging Face and go ahead with it. And we are also going to be installing other things, FastAI, of course, because we don't want to redefine our what do you call, training cycle again and again. So it's very good when it. I mean, FastAI is very good when it comes to that. By the way, before that, I'm gonna need the GPU. So, and from transformers import, and we're actually gonna be using the GPT-2 model. I actually thought of that GPT-3 would be much more. I mean, you would say that why not GPT-3? GPT-2 is quite old. Google Colab isn't simply capable enough to handle GPT-3. GPT-2 still, yes. I mean, it's still very heavy. Like you would see that just fine tuning one epoch takes about an hour to do that. So, but still, I mean, it's a wonderful model. Sorry, I mean, time isn't necessarily defined by that, but I mean, that's the most that the GPU memory will be able to handle. Like, trust me. Anyways, so I'm going to be taking just like the head of, say, a simple GPT-2 model, which is trained on some tasks. So I don't know if we talked about language models. So let's talk about language models for some time. Um, uh, the concept of image pre-training. So like for any sort of like for a very wide amount variety of like image tasks, image generation, image classification, key point detection, what do you call object localization, segmentation, and whatnot, and whatnot. We use the weights from from a single pre-trained model, right? And that is usually, let's say, trained on ImageNet and something and so forth. So, how do you think that like a model that was initially just used for classification tasks can be used for such a wide variety of image tasks? It's because it's usually understood that the final task that needs to be done, classification, key point detection, segmentation, actually comes from the very few final layers, and the vast majority of the layers from the beginning till the like a few layers from the end, they're actually just used to identify the features of images, like edges and colors and like shapes and whatnot and so forth. So it makes sense to it. So the idea of pre-training is that we take out those weights until the very few last layers, and that can be used for any sort of task. And so we use this idea for NLP as well, that they apparently trained a GPT-2 model on, let's say, some huge NLP task, and so now the weights can be used for any sort of language NLP task. And so this is called a language model. And whatever I mean, that part of the model, I mean, a model excluding the final few layers is called the head of the model. So that's GPT-2 language model, head model. Anyways, uh, and because this is already pre-trained, we actually need the tokenizer that they used, because how would we even know that whatever was the we don't know the vocabulary that is used in this language model. So Hugging Face provides us with that as well. Right. By the way, okay. Till then, let's actually also type search, of course, fast AI. So I need to upgrade it because the default version of fast AI is like something like 1.0, and the library is now in 2.0 stage. Fast AI temp, and from fastai.text.all import star. Okay, what's the error? No module name transformers. Oh, transformers. Okay, what's the error now? Uh, all right, so let me actually rerun this because Collab has apparently not figured out that we're still talking about package to what do you call it? FastAI 2.0. Anyways, runtime, factory reset runtime. You actually need to do this with Collab every time, so bear with me. Uh, Yep. Sorry, it works now. All right. So what I'm gonna do is at first I'm gonna build my tokenizer. So it's gonna be so. By the way, GPT-2 tokenizer fast is like uh, you can define like so GPT-2 has been trained on a lot of tasks, right? So you can choose what the from which pre-trained model you want to choose the weights from. So I'm gonna do I mean, the default version, which I'm not exact. I don't remember like which dataset it was trained on, but like it must be a very famous NLP task. But anyways, so by the way, all this is available on their website. Like how do you actually use this? But okay, and I'm gonna use this attribute known as from pre-trained, and I'm gonna pass in the attribute GPT-2. All right, and model is gonna be GPT-2 m head model dot from pre-trained again GPT-2, right? And it's gonna download anything. By the way, this is the maximum. I've tried a lot of different things. This is the maximum that Collab GPU can handle, and I'll actually show you. Oh, by the way, does how do you uh, use show the memory usage? Because apparently Google Colab has a new feature that shows you like which thing is using memory, how and whatnot. Anyways, so it's downloading all its stuff. You can see there is something from 523 MB, but anyways, uh, yeah. See, RAM usage apparently went up. Can we actually? Okay, anyways, never mind. Right. Anyways, let's see what the model looks like. So, oh, and let's also see what GPT-2 looks like. Uh, uh, Arre? Yeah, apparently. Yeah, I'm trying to look for the architecture. Anyways, okay, never mind. This is what the model looks like. So it has very much similar components to a normal transformer that you would see. This is what a transformer looks like. The good thing about transformers is, by the way, you don't need to go sequentially across all the data. Like you can feed in all the data at once, right? And uh, it will, it has mechanisms to understand the sequentiality, and all in all a very extremely powerful model. Go through that paper if you want to, the original 2017 paper. But essentially, what it is, you pass in the input embeddings, of course. That is already provided in the GPT-2 model. You do some encodings on it, right? And then you pass it through attention layers. So if you read what attention is all you need, you would understand what attention is. And then there's just feed forward mechanisms. This is the encoder. It goes to the decoder. Decoder is nothing but the opposite of encoder. So you so it's simply an encoder decoder type architecture. So whatever type of input you're giving, it's going to give you the same type of output. That is the purpose of yeah. And essentially, if you think about it, it's just like modeling an entire language modeling task as a simple neural network type architecture, like a simple CNN type architecture or feed forward MLP layer architecture, in which like you're expecting it the model to understand that whenever this input is given, let's say 1 2 3 4 5 6 7 8 9, without actually going through them sequentially like manually, you're making the model understand that whenever 1 2 3 4 5 6 is the output, 8 is the output, is the 1 2 3 4 5 6 is the input, 8 is the output, or whatever, like that is just uh, extremely impressive, is all I can say, because that just truly shows like how capable neural networks are to understand like very fine level details, like even like relations between like feature between elements of a single vector and so on and so forth. Anyways, so we talked about encoding. Encoding is done by the tokenizer, right? Sorry, embedding. So you have tokens that goes through these embedding layers, right? And then followed by this attention, and then so sorry. This is uh, what do you call encoder, so input embeddings, this is that corresponding what do you call embedding layer, and then it goes through the positional encoding, which is this, right? And then uh, just normal layer norm attention. Attention is nothing but again convolutional layers, and what it does is that it reduces extracts salient features from the images and so on and so forth, and it's trainable as such. Right, and so this is what happens. Anyways, that's the model. It's quite impressive. And let's also see like how the tokenizer works. So I'm going to say that I indexes. Okay. Go to tokenizer dot encode. So this is a function uh, uh, that takes in a string as input and can directly give you the output as token. NLP, and today we are going to study transformers. Right. Let's check what IDs look like. So so you can see that, I mean, this must be the token 1212. Let's actually, yeah, by the way, apparently there are 50,000 tokens now. So in the last problem, we only dealt with like 30 tokens. Now this is a huge jump. Like you can see like how complex the model would be in order to get these things right. Anyways, and you can also do a decode, which is like the opposite of it, to get the what do you call uh, to get the original text back. So tokenizer dot decode, and then you give the IDs back, and this is what you're gonna get. Yeah. This is a lab session NLP, and today we're going to be studying transformers. By the way, you also must notice that it gets like the capital T and small t right, which is again crazy, right? So transform of the T capital, transform of the small t, and some other things also must be like totally independent from each other within this tokenization. Anyways, so uh, since our model is already pre-trained now, you can actually directly use it to get some predictions, right? I mean, without even training, it's gonna give some amount of accuracy. And models, of course, PyTorch models only take tensor, so we're gonna first have to convert it into tensor, and I'm gonna go with long tensor because now we're potentially gonna be dealing with huge amounts of batch sizes and whatnot. Sorry about this. Anyways, um, and I'm gonna do this none technique to create a batch of a single batch, like a batch size one. and we learned about this in the previous class if we don't remember. So this is just gonna create, let's say for example, a tensor of size 16 because so for example this must be 16 words, I'm assuming. Let's see. Yep. And so, but what do you call, PyTorch expects everything to be present in what do you call, batches. So none is going to give me 1 comma 16, which is anyways. So I'm just going to pass it to the model, and I'm just going to do model dot generate the max length. I'm going to say that give me the next 50, or give me 50 tokens at once. That's it. No, by the way, max length is going to be, let's say, 50. By the way, by default, max length is 20. If you don't pass anything, it's gonna give you 20 tokens. But I mean, this itself is like 16 tokens. So like, what is you're gonna get like 4 extra tokens. So, anyways, and let's see what Preds will look like. The reason I'm doing um, what do you call, uh, comma like zero, because spread itself will have like multiple tensors, one tensor corresponding to the tokens, one corresponding to the activations, and so on and so forth. um so I'm going to do tokenizer dot decode at zero, see like what it talks, what it is. This is a lab on NLP, and today we're going to be studying transformers. We'll be using the same transformers as the previous session, but with a different set of transformers. So good, like this is good. And the fact that this is completely new to the model, which is why it might not be good, but it's still good English. Like this is quite plausible, and like to a person like who doesn't read it very carefully, you'll say like, wow, this is wonderful, like it works very well. So let's actually train it now. Let's actually fine tune it to a model. So fine tuning the model, and we're gonna be using the fast AI model, right? Okay, so I'm gonna create a new data set on which I'm going to be tuning this, right? So I'm going to be using a FastAI data set. Let's just use like a Wikipedia text, but a smaller version of that, right? Uh, Wiki, Wiki text time, yeah. And path.ls. Let's see. Yep, yep, it's over here. Anyways, I'm going to be creating. This is actually, this is not one entire sequence of text. Like it contains text from very different articles as different things within these files, within the CSV files. So we need to create. I'm going to first create data frames, and then I'm going to concatenate all them together into one tensor. Let's see what that looks like. Anyways, um, dot read CSV path slash train dot CSV, and by default it does not contain any what do you call it, headers. So why waste one extra row when you can use that data into training? So header is equal to none. Dot read CSV slash what do you call it, test dot CSV number header equals none. Let's see. Right. So um, New York City FC season, the 2013-2014 season was the season of competitive association football in 77th. Let's actually see which Wikipedia article is this because it's quite interesting. Let's see. And I'll show you that this is exactly, yeah, so this is the exact Wikipedia article from which it must have been picked up. Anyways, Okay, so this is the input. Let's actually try concatenating it all into one single text. So I'm gonna concatenate main values, valid values into all into one text, because when you're fine tuning a language model, it doesn't make sense to, unless you want to do classification. Like there's no point in um, what do you call um so, there's no point in um, like having them all as separate what do you call elements. Like these all should not be different data points, because we're anyways. Now, here's the problem with this, that these all may be of different lengths as such, right? So anyways, you can't put them together in a batch as such. Like already you first need to concatenate them, and then you're going to have to divide them into batches, like uh, using the way we talked about. And then we also going to have to look about that group chunks thing that we've been talking about. All this thing is, by the way, like there are mechanisms in fast.ai to take care of that, so we're actually going to look how to do that very easily. So let's just see. I haven't okay. So I didn't import numpy, but fastly already does that. But okay, let me just do that for sake of completeness. Import numpy as an e, empty that concatenate df df, sorry. Okay, let's see what all text looks like. It's going to take some time because it's a big data set. Uh, right. So this is one big what do you call string that contains all this stuff. But anyways, what I'm gonna do is that I'm gonna need to create a data set now. So I would essentially want a data set, but in order to create a data set, first I would need to take a word and then pass it through the tokenizer, right? And then the tokenizer has to be converted into one hot encoded vectors, right? And that has to be put into tensors. So this is like a huge pipeline. So for that, what I'm going to do is that I'm going to create a class, which when that class is called, is going to take an input word and it's going to simply do all those things and like give you one output, right? So I'm going to, let's say, I'm going to define, let's say, class transformers tokenizer, and it's gonna inherit from transformers, which is a base, it's a transform class from FastAI itself, because there's a lot of things that transforms actually need to take care of, and I don't want to write all of that from scratch. But anyways, as always, it itself, it takes in the tokenizer, because that's a property of a tokenizer. Like, and it's gonna have the, like, we're gonna pass it the GPT-2 tokenizer, and it's gonna take care of all that stuff. Anyways, so self dot tokenizer equals tokenizer, right? Um, so the process of taking an input and like giving into a suitable form is called encoding, and doing the opposite is called decoding. So I'm just gonna name it encode and decode, and that's actually uh, faster terminology. So I'm gonna pass it to another class, and it's gonna expect that this class that I'm passing has some sort of encodes or decodes. By default, encodes is nothing but a, like, you give it x and it returns x itself, so nothing is done. And decodes is also the same, but like you can modify it as much as you want. Um, so first I'm gonna create tokens, right? Which is nothing but numbers. Like this would be given the value 1213, and so it has to be created. So first I'm gonna do that. Self tokenizer dot tokenize, and then it has to be created into one hot vectors, and then put into a tensor. So tensor self dot tokenizer dot convert tokens not again tokens to IDs tokens tokens, right? Well, that's that. Decodes on the other hand, so it's gonna take in a one hot encoded vector, sorry, a one hot encoder which is gonna come out from that. I'm gonna pass it to the tokenizer's decode, um, and um, they're probably gonna be strings. Sorry, I'm not exactly sure, but okay, let's actually. Right, this is a string. Um, uh, but I'm not exactly sure, but I think that according to the API, there may be different cases in which a different sort of output may be case. So we'll override that and we'll make it forcefully convert it into what do you call a string. So I'm gonna return titled string. Actually, nothing but um, um, so so if you look at FastAI's definition, it's basically a string with show. So when you do dot show, uh, it's gonna output like a very beautified version of the string instead of like you know whatever, instead of like all these different sorts of things with like um, like things appear on different lines anytime, and then there's different stuff going on over here. So it's actually quite useful. And this I've picked it up from the API. You can actually remove title strings, doesn't matter, but it's better for your own interpretability anyways. Decode. This can be done on the CPU as well. So I'm gonna I'm gonna remove it from the GPU before decoding it. Why use extra memory? And then I'm gonna convert it into NumPy because the tokenizer doesn't understand uh, tensors. Like it's gonna give you an error. It understands NumPy values, and it's very easy to convert a tensor into a NumPy value. Which is why you must have seen that. I mean, I first do not over here, but um, yeah, I first did. Sorry. Okay, never mind. Anyways, that's my Transformers class. So what I'm gonna do now is get my data sets. Right. So I'm gonna create. Um, I'm gonna first define where I want my data to split. Right. And so I can actually. What I'm gonna do is that. I've first combined this entire data into one set, like train and validation set into one. I'm going to say that whatever was the length of the training data set, cut it at that point, right? And then I'm going to use that training data set to divide my training data into equal number of, I mean, equal chunks. That's my point. Okay, so splits equals, I'm going to create a list. I'm going to say range of, which is nothing but a range function. Like you don't have to uh, type in range len df anyways, so it takes care of all of that. And what I'm going to do after that is that this is going to be a list. And now I'm going to create a list starting from a range, starting from the length of data frame of plane until the very end of all text. Right? So range starting from the length of data frame and until the length of all text. So that's the length of the validation part. And um, I'm gonna now use to create my list. I'm gonna use wait, sorry for this. I'm gonna create a list, a variation of list created by FastAI known as TFMD lists. By the way, if you ever want to know like anything about the documentations of FastAI, you can go to docs.fast.ai and it will give you the answer. So you can type in TFMD lists over here, and it basically stands for transformed lists. What transformed lists does is that um, we define certain transformation over here. Right? We define transformations over here, and we um, so what list is going to do that this list is going to apply all those transformations sequentially onto um, onto whatever data set I have. And so what that means is that whenever I'm going to access any value, it's going to take in any input and it's going to apply all those sequences of transforms that I already applied. And it's going to give me the transform value, which is exactly what I want. So I don't have to do any extra sort of effort as such. So um, I create my transform lists, which is going to take all the text. I'm going to pass it.
Palash, sorry, I tried to disturb you. Can you hear me?
Yes.
Sorry, actually, I could not join because there were other students came to me and I was actually taking interviews and I forget to start the recording. So,
No, it's okay. I already, I'm doing recording on my end, so you can see.
okay, okay, then
So
ठीक है,
let's
then
send me the
let's.
recording. Okay.
Okay, thank you. Good. Please go ahead.
Okay. Thank you. So I'm going to pass it the class of transformers, which, by the way, this TFMD list knows that I have to go to encodes in order to take in an input and give me the transformed outputs. And if I ever want to do the decodes, it's going to take in whatever input and it's going to call the decodes attribute of this transform function. So transformers tokenizer, I need to initialize it. Um, so initialize is nothing but I'm going to pass it the tokenizer. I've already defined the tokenizer, which is nothing but the default which I got from the Hugging Face library for GPT-2. I'm going to pass it like where I want my training and testing to begin. So splits equal to splits. Um, and one more, this model is actually capable enough of giving me the data loaders directly. So FastAI actually already takes care of this language modeling sort of data loaders, which is nothing but like creating self-supervised sort of input-output sequences. Like if 1, 2, 3 is the input, 2, 3, 4 will be the output, and so on and so forth. So you don't explicitly have to pass in outputs in order to create your data sets. So language model data loader is just that variation of a normal data loader, except that it knows how to create outputs from the inputs as well. Self-supervised learning. Uh, all right, let's see. We're actually going to get a small error because I mean I passed it a very huge data set all in all together, but our model is going to work. Now the reason why I say so is because when you have very long sequences of data, it's very hard to know where one uh, data point stops and one where data point starts. I mean because now that I've concatenated all these together, there may be many batches, which contain half of that data point will be from one document and half of it will be from other document, and it is necessary uh, because we want to create data points of equal batch. I mean, we want to create batches of equal data point sizes, and each sequence is also supposed to be of the same size. So when you increase the number of data points beyond a point, like the data set becomes very large, that number of ambiguous data points will suddenly start increasing, and that's not good for the model. I mean, like, because there's a discontinuity within that data point, and the model is going to learn that, and so it's slightly bad for the model, but that's okay. This is just a dummy problem, and it's not as bad. I mean, there are models that train on millions of data points, so we're just talking about like 4,576. Uh, all right. So I've created my this data loaders, and I can. So now what I can do is that I can do transform lists dot train, and it's gonna give me. Uh, let's see. Let's see what it gives us. It's gonna give me a list of all the training data points, by the way, and it's gonna be encoded because it has already applied all the transformations. But because I've now, what essentially happens is that um, because whenever I'm, by the way, when I'm doing TLs or train, it's accessing an internal function known as call, right? That's standard Python. Like, that's how classes work. And so what call is doing is that call knows to access the decodes function, because by default it's nothing but tokens, and we won't understand tokens. It needs to be converted back into strings. So it calls this tokens and gives me this text as I would understand it. So that's the functionality that I've created at this point. So that's pretty good. Anyways, let's actually go ahead. Standard training, batch size is equal to. Okay, I think now my data point is actually very large. So I'm going to start with 4. If it works well, I'm probably going to go to 6 to 8, 16 maybe. But I don't think that's going to work, because GPT-2 itself is a very heavy model. It's very RAM, like the RAM usage of a GPT-2 model is like extremely large. And so I think a batch size of 4, I don't expect anything more than that. So I've already created these lists. I'm gonna call the data loaders from this. I mean, it's basically just sequence of all the lists, and now I can call data loaders and ask. So what data loaders will do? It will explicitly divide it into batches now of sequence lengths. I need to define the sequence length as well. So sequence length is, let's say, 256. All right. So this. So BS is equal to BS. Shuffle. I mean, all these defaults are fine. Uh, and sequence sequence length equals SL, right? Let's see. Uh, and so yeah, it's running now. Because this is such a large data set, it takes a lot of time to iterate through the entire sequence. And if you remember, we implemented it as a for loop. So uh, because we define sequence length, so it knows that, like, I have to first jump 256 characters in order to append anything to a batch. So they're like batch BS times SL number of time steps that needs to be computed in order to create this data loader, apart from whatever complexity it takes to append to a data loader using tensors and whatnot. So yeah, that's a lot of computational. That's a lot of time complexity. But anyways, now that I've created my data loaders, let's actually see a batch. So dot show batch, and a batch size. I mean, doesn't matter. Let's see. Yeah. So four batch size is four, so there are four data points. And so you see that this is the input and this is the output that is offset by one value. So records is not over here. So records unknown. Unknown is, by the way, the token corresponding to, let's say, some proper variable in which it doesn't make sense to create a separate token in the NLP dictionary. But anyways, uh, uh, records unknown records in print. So now it's unknown records in print. So we have offset this by one. So this is now our language modeling task, right? Self-supervised learning. Uh, right. All right. So we can now simply like train this into a model, and that's going to be the end of our class today. But there's one small thing that we need to do, and that is that we need to, because we're going to be training a model using the API from FastAI, and it's very generic. But the Hugging Face model has some different attributes, and the only, I mean, it's essentially the same, but the names might be different. So we need to create separate classes that basically say that whenever FastAI's API calls this function, what essentially is happening is that Hugging Face, you need to convert this into this function from Hugging Face, and that's essentially it. Uh, Now, so okay, one thing. So because in general PyTorch, what PyTorch does is that you pass in input and it gives you the output tensor. That's it, right? Hugging Face's model, whenever you pass something, because of the design of their API in general, it passes multiple outputs. Which is why, if you remember that when we did, when we did, when we actually predicted without any training, we had to index the zeroth element of the prediction because it contains activations as well. So this zero had to be done in order to get the outputs, right? So we're gonna have to make we're gonna have to ask our model to we're gonna have to ask create a callback or something like that in order to say that the prediction, if the model wants to get the prediction from this Hugging Face model, access the zeroth element. So that's about it. So I'm gonna create a class. It's gonna be what do you call it's gonna be a callback. Callback is nothing but a function which is called at, let's say, specific training stages. Uh, so it's gonna inherit from callback as which is a parent class defined by FastAI again, because I don't want to define many things like init. Init of a callback remains the same, I guess. Nothing else has to be. All I need to predict is like at what stage I want to call this callback. So I'm going to do after prediction, a prediction of whatever. And so, by the way, you can see like whatever all these stages that exist in the FastAI documentation. And what essentially will happen is that whenever after the stage when the model predicts, FastAI's API is gonna call that for whatever callbacks that you've created, call the after prediction uh, function corresponding to them. And so if I custom define a functionality, that functionality is going to be called at that particular stage of the model and nowhere else. So that's the beauty of callbacks. I'm going to go self dot because callbacks are only a property of the learner class. So you can't directly access, let's say, the models or predictions as such. You can always go to learn and then go to its attributes indirectly. If you remember that what we did was that we assigned, whenever we created the learner class on our own, we assigned our self.pred, stands for prediction, self.prediction as model uh, whenever output of the model whenever an input is given. So that has to be reassigned because self.pred as is like, let's say, a tuple or a list of two or three different values which is given by the Hugging Face model, right? So I'm going to replace it by just the zeroth element of the prediction, which is nothing going to be but the tokens, so that you can now do loss functions, you can do other things very well. Now I can simply just go ahead and create my learner class. It's going to take in the DLs, it's going to take the model, it's going to take the loss function, which is going to be nothing but the cross entropy loss function. Sorry, cross entropy loss flat. You need to flatten it because again we talked about this issue that the each batch is going to look like something like batch size, comma sequence length, comma vocab size, or the number of tokens, which is some 50,000 or whatever. And so cross entropy itself is going to get confused, and so it's going to have to uh, flatten out, let's say, every element except the batch size in order like for the cross entropy to work normally. So that's how. So that needs to be done. And then my callbacks, I'm just of course I'm going to have the the drop output, not dropout. Dropout is different. Um, I think you can use that as of now. And now we're going to talk about this new metric, which is very useful in NLP tasks, which is called dot perplexity, which is because I told you that accuracy is really not a good measure for language models. Because I mean, what's the probability that exactly this output is going to be predicted given that the sequence is now 256 tokens? These are like, by the way, 256 tokens. What's the probability that the language model is going to give exactly this answer? I mean, even if it gets the entire context right, which itself is very rare and still not extremely wrong. But let's say that I mean it gives synonyms, let's say, or rearranges certain words. It's still not wrong as such, and so the accuracy shouldn't like go completely haywire because of that. And so what we do is that even though the words are not right, but like the aggregate of the activations, it's like the values of activations. The purpose of activations is to like give a general idea about the context of the model, if you think about it, because it's nothing but a statistical distribution, right? Activations represent a statistical distribution, and so like in a very like it may not be mathematically true, but if I were to give you a very good general idea, the general idea about or the general context of a given text can be determined by the activations in general, like the distribution of the activations in general. Perplexity is nothing but whatever token is generated. So, for example, put all its, and then the next corresponding token is going to be ground, right? Uh, Whatever corresponding token you have, we because activations can be positive or negative, so we first need to do an exponential, just like we do in softmax, and then you see like what um, perplexity is defined as. Well, let me go to my Jamboard. It's simply defined as e to the power of x. X is nothing but the prediction of the token whichever I've used now. And this is nothing but the softmax function essentially, right? So this is going to be x correspond is the token corresponding to the word ground, for example. And the lower the perplexity, the better the prediction. That's how it works. So, anyways, um, and by the way, because this is such a big model, I essentially like to reduce the what do you call precision. Two reasons, because by the way, precision is by the way nothing but the amount of decimal places that are occupied by each tensor within the GPU, right? It is found in deep learning that deep learning necessarily doesn't need that much of a precision. So ideally, like in every task, it's okay to reduce the. So by the way, now you have 32-bit tensors and like 64-bit computational CPUs and GPUs. You don't need 64 bits, and so you have an option to reduce the number of floating point in decimals in your GPU. How it helps is that I mean, like ideally, like any task would work if you reduce the amount of what do you call if you remove the what do you call precision of the GPU, because you don't need that much precision for deep learning models, which is why TPUs exist, tensor processing units. Tensor processing units are nothing but GPUs with lower precision. That's the entire point of TPUs. But we didn't have to do it because we didn't actually face such large models. But now we're actually dealing with something like GPT-2. It's good to take such measures. We're not using accuracy because accuracy is not a good measure. Before actually training, let's actually see what kind of results we're gonna get. So it's gonna take about 2 minutes or so. Because by the way, It's such a big model that even like, by the way, the validation task in the previous task took like something like 1 second, 2 seconds or something. This is taking like something like 2 minutes. That's actually quite computationally expensive. uh, so because the model is so big, the data set also is so big, so it takes time. But what I'm trying to show is that like this is what perplexity, the value of perplexity will look as of now. Because if we're talking about exponential, so it's going to be slightly big, so something more than you'd expect, something like in the orders of 10, 20, 50, 30, 40, 50. And I'm going to show that after training it's going to reduce after to a good point, and that's good. We can't wait for the entire training process. It's going to take about an hour, but I'm going to leave it to you. You can run it, and then see, you can go take a walk, have dinner, have lunch, and then come back after an hour. You'll see that the perplexity has reduced, so that's good. Oh, one more thing actually, I'd like to use a regularizer. Like, we learned about weight decay and regularization as such, right? If you remember. Because this is such a big model, that's also a good thing to use. So first actually defines a regularizer. Regularizer, right? I'm going to be initializing that as well after that. And then after that, we're going to simply do learn dot fit one cycle, which is a variant of the normal fit function. It uses something known as cyclic learning rates. So it's basically scheduling of what do you call, the learning rate in a cyclic fashion. So it slowly first increases, and then in the later half of the epoch it reduces. Apparently that increases the accuracy. It was proposed by Leslie Smith back in 2018 or something like that, I remember. So by the way, this is the activation values softmax, and this is the perplexity value, which is 40.29 or something like that. I'm gonna do learn out fit one cycle, one epoch, and let's say a learning rate of 10 to the power minus 4. Let me leave it for training. It's gonna take 44 minutes. I'm not gonna make you stay until then. Let's actually, once you do that, why don't you actually look at the performance of this model, which is gonna say that actually I'm just gonna go and let's say, yeah, this is the input sequence, for example, and let's say prompt is equal to this. I'm gonna say that because I need to first convert them into what do you call, uh, index as one hot encoded vectors. I'm just gonna do tokenizer dot encode. Encode is, by the way, it takes care of tokenization as well as indexing into one hot encoded vectors. We looked at this prompt. Input to the is going to be the tensor version of that. So tensor prompt IDs. You need to convert that into a batch, put it into a GPU. So CUDA, right? You can take a look at input shape, for example. I usually do that just to make sure of that. Then you just simply do threads equal to learn dot model dot generate. Hugging Face model actually have the generate function instead of the predict function as we usually looked at. So that's okay. We can take care of that. Generate has general properties we looked at before. 50 tokens. Um, how many threads do you want to use? I'm gonna say 5. That's perfectly okay. Uh, Apparently there is something, a standard value that of temperature. I'm not exactly sure what this does, but let's take a look at temperature. Um, Temperature. No, not data sets. GPT-2. Uh, PyTorch. Oh, by the way, so Hugging Face will give you the TensorFlow version, PyTorch version, JAX for deployment and whatnot. Uh, Oh, damn. Yeah, here's the GPT-2 model. Uh, dot generate. Where is the documentation? Uh, okay, you can take a look at it, but yeah, I want that repository. Okay, this is confusing, but anyways, take a look if you want. Standard values, anyways, and tokenizer. I mean, it's gonna give you some tokens. You do decode in order to see what it looks like. It's zero because yeah, dot CPU, of course, and dot numpy. We've already looked at this. So all this, and you're gonna see that it's much better. It's amazing in comparison to that. Complexity will have reduced to quite a good value. I'm assuming around 15, 16, something like that. But this is how you work with transformers. So um, and it's as easy as that. We didn't do many changes. We only took the pre-trained transform model from Hugging Face or any other library. There are amazing n number of libraries that provide you with pre-trained models or with architectures in general. And then all we did was we defined some extra few functions that integrate the FastAI API and the Hugging Face API only because like certain functions which are the same functionality occur with different names. That's all. And we use the tokenizer from the pre-trained model as well because if you're using a pre-trained model, it's also important to use the tokenizer from that as well. That's tokenizer and that's NLP for you guys. Hope you guys enjoyed it and hope you guys can use it to some good use. You can build some good projects with it. And